Good morning to all our friends and colleagues that are in Italy, and good afternoon and good evening to our Japanese friends. I am Giorgio Starace, and I am the Italian ambassador here in this fantastic country that is Japan. Dear speakers, dear participants, it is today a great honor to present my greetings at the opening of this webinar towards climate neutrality within 2050, Italy-Japan approaches to hydrogen deployment, organized by the Embassy of Italy in Tokyo through our scientific counselor, Professor Enrico Traversa, that to goes all my gratitude, because it is a very special occasion for all of us. This event, in fact, is part of a series of webinars that we have, the Embassy of Italy in Japan, we have launched on scientific and technological cooperation between Italy and Japan, and follows the first one dedicated to COVID vaccines and therapies. It is the first, this one on hydrogen, of 3 events we are organizing and dedicated to the global challenge of climate neutrality within 2050, and will also be followed by web conferences on other relevant topics for bilateral cooperation in science and technology, for example, in space technology, and several others webinar will follow this one on always on renewable energies. The recent announcement of Prime Minister Suga of the new Japan engagement towards zero emission within 2050 has opened an intense discussion within the country about how to achieve this strategic goal and its economic viability. Prime Minister Suga emphasized that the 2050 goal would offer to Japan new opportunities for dynamic economic development. The kick has started an increasing, unprecedented national commitment to boost investment in technologies to tackle climate change and to turn renewables into a primary energy resource. Hydrogen development is emerging as one of the fundamental tools in this endeavor. Research on hydrogen in Japan has been at the forefront since decades, and the recent acceleration of industrial implementation is certainly welcomed by scientists. Our distinguished Japanese speaker, Professor Sasaki and Mr. Matsuda, are outstanding examples of the 2 phases of research and industry. Thank you for being today with us. Hydrogen research in Italy is also worldwide prominent, as well as industrial applications. And we are having today remarkable examples with Dottor Aricò and Dottor Montinaro. Grazie per essere con noi oggi. I am proud to represent a leading country in the use and production of energy from renewable resources. This engagement is reflected by the fact that Italy, a founding member of the European Union, is co-hosting the COP26 with the United Kingdom and holds the G20 Presidency, where climate change issue will have a paramount role. The 2 introductory talks of Dr. Bazzani and Dr. Longobardi will briefly introduce the Italian policies, and also thank you, Mr. Longobardi and Mr. Bazzani, to be today with us. Thank you for your presence. Aim of this event is to update about the hydrogen-related technology in Italy and Japan, thus exploring the possibility of further collaboration and synergies. I am sure that you will enjoy the webinar. I wish you a very fruitful discussion and a stimulating learning experience. The future of the cooperation between two very advanced economies as the Japanese and the Italian one, two countries that are in the future and that are leader in many top-level technologies, is to find the ground of cooperation also at industrial level for joint programs. And these webinars are a vehicle to promote this cooperation. Space, artificial intelligence, robotics, renewable energy, medical applications to aging societies. These are many of the examples on which we want to insist. Thank you very much for your attention. So now I am very pleased to introduce Mr. Nicola Bazzani, who is going to be the first speaker, Deputy Head Office, Energy Environment of the Ministry of Foreign Affairs and International Cooperation of Italy. Please, Mr. Bazzani, Councillor Bazzani, the floor is yours.
Mr. Ambassador, thank you very much indeed. Good afternoon, everybody from Rome, dear colleagues, dear friends in Tokyo. I'm going to give you a very quick snapshot concerning the priorities of the Italian G20 on energy and climate. As you can actually see in front of you and in my marvelous virtual background, the symbol of the Italian presidency this year is the Vitruvian Man, the very famous drawing from Leonardo, representing the man and its perfection within the space, within the planet we are living in. And what better example of the nexus, energy and climate, for a more prosperous, livable reality than this. We intend to make, for the very first time, of energy and climate a driver for development, a driver for sustainability, accelerating the clean energy transition and halting climate change. Next slide, please. This is the decision why this year we have decided to have the energy transition and the climate sustainability to work hand in hand together towards the first ever joint energy and climate ministerial meeting. That is, we have decided to elevate to the podium of the ministerial meeting the climate change issue together with energy, because as you know very well, energy is, as of today, responsible for around 2/3 of global GHG emissions. We have invited a set of special actors, in particular from the Asian region, and in particular Southeast Asia, just to remark the importance of that part of the world, like Brunei as chair of ASEAN and Singapore as well, together with other countries representing the African Union, Nepal, and some special invitees, Spain and the Netherlands. Next, please. In a snapshot, we have decided to harness three main tools to develop our narrative towards a future with net zero emissions. And by the way, as the ambassador reminded, the commitment, the political commitment of the Japanese Prime Minister for a carbon neutral economy by 2050 is very much welcome for us. We believe that never before, as this moment is in history, there is a political momentum to reach such an ambitious target. How do we intend to do that? Developing sustainable, smart, and resilient energy cities for the future, advancing towards a sustainable green recovery, seizing the opportunities offered by innovative energy technological solutions with zero impact on the climate change, and also taking advantage of this tremendous crisis of the COVID-19 to accelerate the alignment of global capital flows towards the green transition and energy inclusivity. And when I say energy inclusivity, I mean two main things: fighting the lack of access to energy and eradicating energy poverty. As we know well, energy poverty is not just something that is affecting non-mature economies, but also mature economies. Secondly, energy inclusivity means also a new concept of energy security. Energy security is not any longer just the demand supply of oil and gas, but embraces the availability of hydrogen, as the ambassador reminded, hydrogen from decarbonized gas, but also green hydrogen, in particular from renewable resources. It embraces power grids, digital systems, in which Italy and Japan are leaders and have much more opportunities to develop this sector. It embraces also critical minerals for the renewables industry and much more. Next, please. It's a very daring challenge that we intend to develop throughout 4 months of full work from March towards the first ever ministerial meeting in Naples. You will see that we have articulated our work in 3 main legs, as I've just defined, and hopefully we will have a ministerial meeting in Naples just in person. As we are also very pragmatic persons, beside having these, as I said, political ambitions towards a future with net zero emissions by mid-century, we have thought about specific deliverables, outcome documents, concrete assets that we can use together to that end. The next slide will show you what I'm talking about. It's kind of a crowded slide, but I will guide you through very easily. We are thinking to have an action plan about urban realities and cities as a deliverable, which clearly draws a line between the energy transition and climate change. We intend to have another joint document that is a set of recommendations for our governments, easy actionables on sustainable recovery plans at global level, given the opportunities offered by the clean technological solutions, the green circular energy economy, with a view to reach our common energy and climate targets. And on the energy specific, we intend to highlight the importance also of ocean energy and offshore renewables. We are aware of the importance of those technologies for a country like Japan and for a peninsula like Italy. So that's why we decided also to invest efforts in ocean energy, offshore renewables, wind, solar, and much more. Energy circularity would be a key asset also for our work. And as I said, energy poverty eradication and a new concept of energy security. Besides, nature-based solutions for the urban environment to halt climate change and reverse the increase of temperatures worldwide, and also a set, and I'm concluding, of options to help the government to increase and speed up the government-owned spending to align their policies to the Paris Agreement objectives, in order, in other words, to boost the private sector in order to have an apt climate finance tools for the future of our planet. Having said that, I'll stop here for time's sake, and I'm handing the floor over to my colleague Bianca for any insightful presentation on the COP26.
Good morning, Mr. Ambassador. Good morning to all. I'll just wait a second for the slides to come up. First of all, for having me here and speaking at this important event. I'm going to just give a brief presentation on Italy's priorities in view of COP26 and beyond. Next slide, please. So as you've heard, Italy and the UK will hold the presidencies of the G20 and the G7. So hosting COP26 in partnership will hence offer a unique opportunity to fully take advantage of the synergies between the different fora. The 26th Conference of Parties of the UN Framework Convention on Climate Change will have to unite the world on a path to zero carbon economy as we build back greener and from COVID-19 in a way that is also fair and inclusive, because the scientific community has confirmed that the past decade was the hottest ever recorded globally, underlining, however, that there's still time to tackle the threat if actions are taken swiftly and decisively. The actions taken in 2021 will very likely shape at least the next decade of climate and energy transitions and play a crucial role to reaching net zero by 2050. Next slide, please. So in parallel to a green recovery, we have to be keeping an eye on filling the ambition gap. So we would need more ambition and mitigation as the nationally determined contributions, the voluntary commitment that countries take in line for with the Paris Agreement still fall far short of the temperature goal of the Paris Agreement and of what science is telling us that is needed. At the same time, we would need more ambition on finance in order to deliver the 100 billion goal of the international climate finance that was promised in Paris, as well as more ambition on adaptation and resilience. At the negotiating level, we need to agree a balanced package for COP26 that helps deliver the Paris Agreement. And we need to do all this taking into account the fact that public expectations have increased dramatically since Paris and that the world is watching. Next slide, please. So, given these challenges, what have we been working? We've been working mainly through ensuring EU and domestic leadership, through civil society engagement, and through climate and energy diplomacy, so international engagement and partnership building. In order to drive international collaboration, the COP26 presidency, the UK, has launched a series of thematic campaigns on adaptation and resilience, on energy, on transport, on nature, and finance. At the same time, we've been working in partnership with the UK in order to build international consensus in view of the negotiations, because as you may know, COP26 is the conference that 5 years after its signing is supposed to deliver a fully operational Paris Agreement. And that means also tackling the issues that were left unresolved last year at COP25 in Madrid. All the same, by COP26, ahead of Glasgow, countries are supposed to submit their revised NDCs, the nationally determined contributions, as well as their long-term strategy. So to that end, international engagement has been aimed in partnership with the UK at seeing evidence of strong national action. And all these comes together in order to reach the Paris goal, which I recall where still are reducing emission, adapting and building resilience, and mobilizing finance. Next slide, please. Under the partnership agreement for the COP26 presidency, Italy will host a series of preparatory events. In particular, we will host in Milan the pre-conference, which is the preparatory meeting for ministers, which is traditionally held about a month before the COP, and has the aim to offer ministers representing the main negotiating parties an opportunity to informally discuss key political aspects of the upcoming conference. And so it's a relevant step in order for the negotiations to succeed. We will also host in Milan, always in Milan, back to back, an event called Youth for Climate Driving Ambition, which will be linked to the pre-COP and will give young people from all over the world the opportunity to draw up concrete proposals, which will be then taken into account by the pre-COP and COP26. Next slide, please. So we've decided to join the two events, as I was saying, because we believe it is crucial to promote the engagement of young generations and channel in a positive and constructive ways the youth mobilizations that we see all around. Furthermore, we will host in Rome in October a high-level ministerial outreach event on environmental and climate challenges in Africa. The idea in our vision is that all these events should be an opportunity to broaden the perspective of the theme of ambition to all the actors involved in global climate action. So in addition to young people, civil society, the business world, the academy, local authorities, and regional institutions. Thank you. Next slide. I will give the floor to Professor Enrico Traversa.
Thank you very much, Bianca. Thank you very much for the introducing with this talks about Italian policies on climate change in forecasting the G20 Presidency and engagement in COP26. So now we are passing to the scientific part of the webinar. And before, I would just make an announcement for housekeeping. So we are holding the question and answer session at the end of the talks. And I encourage the participants to submit questions in the Q&A panel in the chat. I'm not sure that I will be able to make all the questions depending on time constraints, but I will surely have a look and try to satisfy the curiosity of everybody. So now we can start without further ado. We can start with the presentation of Professor Kazunari Sasaki. Kazu is a director of the International Research Center for Hydrogen Energy and vice president of Kyushu University. And he's working since many years on hydrogen. So we are very eager to listen to his talk. Please, Kazu.
So I'm preparing my slide. Yep. Can you see my slide?
Yes, everything is fine.
Okay. So thank you very much for kind introduction. Thank you very much for Mr. Ambassador, my ladies and gentlemen. It's my great pleasure to give this presentation. First of all, thank you very much for invitation. And of course, I know Enrico since almost 2 decades. And it is nice that you have organized a very nice event. So my name is Sasaki from Kyushu University, but I spent for 10 years in Europe. So I will also talk about the hydrogen energy with the Japanese perspective, but strongly influenced by the European mind. I spent for more than 5 years in Switzerland, and I think that some of our colleagues also joining the Italian company developing solid oxide fuel cell and solid oxide electrolyzers. Yeah, let me start my presentation. I'm actually talking about giving this lecture almost 1,000 kilometers far from Tokyo. We are now in we have the largest university campus in Japan. And this is also somehow like the German style research team already established in Japan. And we have the very strong activity in the hydrogen energy research. So this slide, I just cited the one slide published by the Hydrogen Council, the Council of the major global companies. It is clearly stated in this slide that if we do nothing, of course, the CO2 emission will be strongly increased. But of course, we can also do many things, including the increase in energy efficiency, but also carbon capture, storage, and utilization is of course interesting to decarbonize and reduce the CO2 emission, of course. And we should also switch to zero emission energy carriers, and electricity is also one option. And but of course, hydrogen of today's topics is also increasingly important. And we also hope that renewables replace the fossil fuels. And that is also a very great challenge, even though we have still this 3 decades left to meet this target. Yeah, increasing the number of global companies has a strong interest in the hydrogen technologies. You can also see which company has been also involved in such the council, but also they have also already declared that hydrogen could also contribute to almost 20% of the CO2 emissions reduction target by 2050. So it is, yeah, potentially is very high, but of course it is not so easy to meet such a target. Especially almost 5 years ago, many of you have also excited about the new fuel cell vehicles. For example, in Japan, Toyota has released on the commercialized fuel cell vehicles by 2014. At that time, many of you or many of us had a feeling that hydrogen is something for the fuel cell vehicles. But I think since a few years, the reason why this hydrogen is important has been also gradually changed. This is also one clear slide, also published by the Hydrogen Council, that hydrogen is also regarded as important chemical energy carrier to introduce more renewables. And that has been also considered for the power generation. Other important advantage of hydrogen is that we can also realize so-called energy coupling, sector coupling. So if the hydrogen is produced from renewables, such hydrogen can be also used for different applications. And hydrogen can be also act as a buffer against the fluctuating renewable electricity. So such green hydrogen we also use, of course, for transportation, but also industry energy application and building heat and power. And the hydrogen can be also used for the feedstock. These are the reasons why, especially countries like Europe, has an increasing interest in hydrogen energy technologies. Yeah, I would also like to mention the history, how the Japanese government has also changed the energy policy in hydrogen. I think Japan is the first, or one of the first country, which has clearly established a roadmap for hydrogen and fuel cell technologies. This roadmap has been issued in 2014, yeah, almost 7 years ago. And I was also involved in this meeting, or the committee meeting to establish this roadmap. At that time, we have already developed a residential fuel cell. Actually, the Toshiba Matsuda-san was also strongly contributed to the development of these technologies, who give also a presentation later in this webinar. We are very happy that the fuel cell vehicle has been commercialized, and in 2017, so we can now we can buy the commercial and industrial fuel cell for industrial applications. Yeah, hydrogen price is still somehow expensive, but we have also set a clear target to reduce the hydrogen price. And from this fiscal year, the big national project has been started to reduce the cost of the fuel cell vehicles. So the company like Toyota and Honda is also working hard, And we have also nice collaboration with such automotive companies. Yeah, in the middle of 2020s, maybe 25, we hope that hydrogen price will be also reduced down to, for example, 30 yen. Currently, 100 yen is the price. But of course, if the hydrogen prices go down to 30 yen, we can also expand the applicability of the hydrogen technologies. And around 2030, hydrogen may be also imported from the overseas. Because Japan is a relatively small country, so we must also import a huge amount of energy resources from overseas. And we hope that we can import the green hydrogen rather than blue hydrogen. And but of course, we are also developing the technologies. For example, the ships for hydrogen transportation. And by 2040, we want to introduce more the green hydrogen, and that is also a great challenge for our countries. After the 3 years, we have revised the scenario for basic hydrogen strategy. This is also a public national paper, but it's, you can also see clearly the number of such target. It is important for private company because the government has the clear target, then the private company can also consider their strategy, and they can also make the long-term investment to develop such technologies. For example, hydrogen volume is also stated, and the cost of the hydrogen is stated. For example, currently $10 per kilogram, but in the future, $3 per kilogram, and in future, we will also reduce the hydrogen price down to $2 per kilogram, with which we can also realize or start the power generation using hydrogen, or the hydrogen carrier like the ammonia. Of course, mobility is one of the important applications, and we can now buy the fuel cell vehicles, but many countries has realized that FCV is the promising technologies, not only for private vehicles, but also for commercial vehicles like buses and trucks and trains and so on. And we are also moving to this direction, and the company, several companies has also started to develop such commercial vehicles. And especially in Japan, we need also electricity and heat at houses. So residential fuel cell, like the Aisin farm, is become also a popular product. And solid oxide fuel cell and polymer electrolyte fuel cell can also contribute to such technologies. Yeah, as the ambassador has mentioned, that Japan has declared carbon neutrality by 2050 by our Prime Minister Suga. That was very surprising declaration. So now the atmosphere has been completely changed in our countries. And that was also a paper published in the December 25th, that is the day of the Christmas. And but I think I cannot find the English version of this policy paper. So you can also see some Japanese word in this slide. But it is clearly stated that we should also reduce the CO2 emission from electricity or the power generation. We should also reduce the CO2 emission related to fuels and feedstock. It is clearly stated that by 2050, electricity must be also produced, of course, by in the decarbonized manner. Maybe 50 to 60% should be renewables, and 30 to 40% should come from either nuclear or the fossil fuels, but combined with CCUS, carbon capture, utilization, or the storage. And it is very nice for me because that was our first paper, official government paper, which has clearly stated that hydrogen or the hydrogen carrier like ammonia, we also produce the 10% of the whole electricity in our countries. That is the first paper, but it is very surprising. But it is a very tough target because we should also produce the hydrogen in very cheaper way, and the mass production is important. So engineers and researchers should also work hard to realize that such target. Another important change is that we should more electrify our country and society. And the energy demand, electricity demand will be also increased up to maybe 30% or 50%. But of course, we need certain fuels and CO2-free feedstock. So hydrogen and also renewable methane, synthetic fuels, and biomass must be also introduced in the whole society by 2050. Yeah, that is official paper, and I think government officer will also use the English version in the official meeting. For example, G20 is hosted by your countries, and it is very nice for such a continuous discussion. So hydrogen is something important, becoming increasingly important, because until now we have the electricity and heat widely used as a secondary energy carrier. But now we can introduce the hydrogen as the third secondary energy carrier, but also a chemical hydrogen energy carrier. And that becomes possible because industry has, in Japan, also around the world, have developed the fuel cell and electrolyzer. And of course, we have started to introduce the hydrogen infrastructure like the hydrogen refilling station. So hydrogen is not something in reality, and we hope that Japan can also continuously contribute to that type of technologies. Hydrogen can also use for combustion technologies because now we are discussing that, for example, hydrogen gas, we also mix with a natural gas-based power plant, or ammonia may be also introduced in the coal-based power plant. So such power plant may be also continuously used, but gradually we can also realize the decarbonization of such a power plant. But of course, as an electrochemist, and Enrico is also an electrochemist, we are very happy that fuel cell technologies will also continuously advanced. Now in Japan, we can also buy the residential fuel cell farm. We can buy the fuel cell vehicles, and larger scale fuel cell become also increasingly important. I think the solid power is very active in Italy in this area, and I'm very happy to hear their presentation. And of course, transportation is one of the important applications of the hydrogen. For example, Toyota has already announced the second generation Mirai, and actually Kyushu University had already ordered this Mirai by December. So if you come to Kyushu University, you can also enjoy the drive of the new Mirai, but first generation Mirai, and also Honda Clarity. But after COVID-19 pandemic, hopefully we can also meet that in our Ito campus. Yeah. In addition, I should also mention that increasing number of companies had interest to realize the commercial vehicles with the fuel cell technologies, and that is very challenging area where, for example, countries like China, but the United States and also European countries has strong interest for such commercial vehicles development. Even though the fuel cell vehicles need also time, because we are also developing, for example, mass production technologies. It takes also time, but with time, we can also increase the fraction of fuel cell vehicles. For example, IEA expected that by 2040, FCV may be 9%. 9% is very small, but improving the developing the mass production technologies is also very, very tough, great challenge for fuel cell engineers and researchers. I hope that I think both type of fuel cells, polymer electrolyte fuel cell and the solid oxide fuel cell, can also realize the wide application of such electrochemical energy systems. For example, polymer electrolyte fuel cell is very nice for automobile application. but a company like the Airbus had already announced the airplane using the hydrogen. This is very interesting topics. And also solid oxide fuel cell is also promising technologies. Or we are saying that hydrogen ready technologies, so that hydrogen can be also used for the solid oxide fuel cell, but other, for example, like renewable methane and the biogas and so on, can be also used by solid oxide fuel cell. So SOC is also included as hydrogen ready technologies, and using both type of fuel cell, we can also contribute to the decarbonizing of the technologies. We can buy the solid oxide fuel cell in countries since more than 10 years. For example, current residential fuel cell can also generate with energy conversion efficiency beyond 50%. And the company guaranteed no maintenance during 10 years. And the reason is that we have understood the durability of the solid oxide fuel cell. Now the product is in the market. Yeah, it is also very challenging to work in this area because larger scale application of fuel cell is interesting. For example, that is one of the first system installed in our campus. I'm also standing here. I was always very happy. And also we are also continuing such the commercialization in our countries. I hope that other various technologies should be also developed to combine with fuel cell technology to realize more efficient energy systems, but carbon neutral energy system and also carbon free energy system we also developed in the future. If you want to understand why Japan has so strong interest in the fuel cell and hydrogen technologies, please read our book published 5 years. And you can find also Japanese secret why we have the very strong interest for such a kind of technologies. Now, even though the application is still limited for automotive and residential applications, but we are expanding the applicability of fuel cell technologies. For example, in this fiscal year, the government has started the new project for the fuel cell for marine application. And the government has also set the great importance of hydrogen for the airplane application. So I hope that such ecosystem of the hydrogen fuel cell will be also expanded, where the both countries can also make also certain collaboration. So even though still we are using the so-called gray hydrogen, because most of the hydrogen is still produced from fossil fuels, but we are also developing the fuel cell and hydrogen infrastructures. So we hope that we can also simultaneously make the transition from gray hydrogen to blue and especially green hydrogen, and that may be also solution and ultimate solution in the future. And that must be also realized by 2050. So thank you very much for your kind attention. I'm very happy to be involved in the panel discussion. Thank you, Enrico.
Thank you very much, Kazu, for your very comprehensive talk. And then we can move to the talk of Nino Arricò to see the perspective for hydrogen production from the Italian side. Nino Arricò is the newly appointed director of ITAE, Institute for Transformation of Advanced Energy Technologies, Nicola Giordano of the National Research Council of Italy. Nino, the floor is yours.
Thank you, Enrico, for your kind introduction. Thank you, Mr. Ambassador, for your kind invitation. It is a pleasure for me to be here today with you to discuss about hydrogen technologies. I don't know if you can see my slides.
Yes, everything is okay.
Thank you. So my presentation of today is dealing with advanced electrolysis technologies for green hydrogen production and uses of hydrogen. And I will essentially focus on projects that have been carried out recently at the Institute of Advanced Energy Technologies of the Italian National Council of Research. Like the previous speaker, I will start with a short introduction about green hydrogen generation and use on a wide scale. As you know, we can produce hydrogen, green hydrogen, from the surplus of renewable energy from photovoltaic and wind energy, and we can use water electrolysis to produce hydrogen from renewable electricity. So electrolysis is the core of this transformation from renewable electricity into chemical energy. So the produced hydrogen can be used in different sectors. In principle, we can inject hydrogen into the gas grid, into the natural gas grid, in power-to-gas processes to progressively decarbonize the gas grid. Green hydrogen can be immediately used to replace gray hydrogen in the industry, in the ammonia synthesis, steel making, methanol, hydrogenation processes, and so on. But if you consider the premium market for hydrogen, for green hydrogen at the present is especially regarding sustainable mobility. So we can use a fuel cell to produce again electricity from hydrogen, and this hydrogen can be fed in cars, in buses, trains, boats, and so on. Hydrogen can be also used in stationary generation in combined heat and power using high temperature solid oxide fuel cells. So all these aspects are part of the so-called hydrogen economy. And I would like to mention briefly that the Ministry of the Economic Development in Italy and the Ministry of Research have already released the agenda for hydrogen deployment strategy in Italy that is covering all these aspects: industry, power to gas, mobility, stationary generation, and so on. Today, I will discuss more in detail some technical aspects of electrolysis technologies. You know that we have a consolidated alkaline electrolysis technology, but in recent years, polymer electrolyte membrane electrolyzers have become very important in this field because of the excellent dynamic behavior that allows the systems to operate in combination with intermittent renewable power sources. Using these systems, we can achieve extremely high current density, extremely high performance, high hydrogen purity, operation at high pressure, because we need pressurized hydrogen to achieve high energy density. However, there are significant drawbacks still to overcome in order to make the system economic competitive and to widely address the conversion of electricity into hydrogen. We need to accelerate the oxygen evolution reaction by using enhanced electrocatalysts. We need to operate at a high current density to reduce capital costs, and we need to reduce the critical raw materials and improve membrane properties. In the FCHJU ElectroIPEM project, that is a European project that I had the honor to coordinate, we have introduced for the first time the Italian produced aqueous membrane produced by Solvay Specialty Polymers into the field of PEM electrolysis. This membrane has enhanced properties in terms of lower equivalent weight, higher range, or a wider operating range, and higher conductivity. And we have also introduced improved nanostructured electrocatalyst in place of conventional electrocatalyst to increase the performance of PEM electrolyzers. And the enhanced efficiency of this new membrane produced in Italy was assessed by our colleagues at ITM Power in UK in the framework of this European project, and reinforced the membranes can allow operation at high differential pressure in the context of electrolysis. In the framework of this project, of this European project, we have assessed the interfacing PEM electrolyzer with the intermittent power profile from renewable from wind turbines produced by Tozzi Renewable Energy, and we have shown that this advanced technology can operate with excellent dynamic behavior, sustaining something like 10,000 start and stops without relevant degradation and with excellent Faraday efficiency. In the subsequent European project, HPEMZGAS, that was also coordinated by myself, we have addressed the ambition to increase the operating current density from 1 to 3 amperes per centimeter, while maintaining cutting-edge efficiency with an efficiency of 80%, energy consumption lower than 50 kilowatt-hour per kilogram of hydrogen. We have introduced this new advanced electrocatalysis and membranes into MEAs produced by IRD in Denmark, and these were integrated into PEM electrolysis stacks produced by ITM Power. And we have demonstrated that this advanced stack technology, this is a 200 kilowatt stack based on an advanced design. You can clearly see in this case there are no tie rods. This is using a new hydraulic compression technology. And using this approach in the framework of the HPEMZGAS project, we have achieved 80% efficiency at 3 amperes per centimeter. This stack has been integrated into an electrolysis system, and this was demonstrated in Emden in Germany. Why in Emden? Because in this municipality there is a large wind power plant and producing a surplus of renewable energy. There is about 240 megawatt-hour of energy produced per year, exceeding, you can see the green curve is the load, the blue curve is the power generated by the windmills. So you can see there is a surplus, a significant surplus of renewable energy, specifically in winter time. And this means that in order to avoid that this surplus of energy is lost because it cannot be accepted by the grid, this should be converted into chemical energy. And we have installed as a proof of concept in Emden, in the framework of this EU project, an electrolysis, an advanced PEM electrolysis system, 200 kilowatt, that is, can you see connected, you can see is connected to a gas uptake station in order to inject directly the hydrogen into the natural gas grid. And in this field testing activity using this advanced PEM electrolysis stack technology, we have shown excellent performance in terms of low energy consumption per kilogram of hydrogen produced, about 50 kilowatt-hour per kilogram of hydrogen, especially at high current density. Now, the new technology, the new frontier in this field is regarding anion exchange membrane electrolyzers. This is still a PEM electrolysis technology using a membrane separator operating at high pressure in order to avoid energy consumption in the in order to reduce energy consumption in the post-compression process. But this new membrane is based on an anion exchange process. That means protonic membrane is replaced with this alkaline membrane, and we can replace all precious metals with non-precious, non-critical raw materials, and we can replace titanium, bipolar plates with cheap stainless steel. So using this technology, we think we can reduce the capex of electrolysis technology from more than 1,000 euro per kilowatt to about 500 euro per kilowatt. Now I will briefly discuss about end uses of green hydrogen. Our institute is strongly involved in developing PEM fuel cell stacks for automotive, for stationary generation using green hydrogen. This is the evolution of PEM fuel cell stacks in our institute, based on advanced platinum alloy electrocatalysts and new membranes. Our collaboration with Solvay has shown capability to operate these PEM fuel cell stacks at a high temperature, covering a wide range of temperature. And we have filed a patent together with Solvay on using radical scavengers in order to improve membrane stability over time. Just a few slides about demonstration projects that have been carried out by our institute. I'm referring especially to some regional projects. The iNext project we have developed in a small municipality in Sicily, in Cabo d'Orlando, an hydrogen valley, a small hydrogen valley that was based on a photovoltaic plant, electrolyzer, and refueling station, and we have produced in this context green hydrogen to refuel small city buses that are currently used for recreation activities. And especially we have focused on the hybridization concept, hybridization of fuel cell systems with the battery systems inside the balance of plant of this automotive system. So these are city buses that have been developed in the framework of these regional projects, and these are examples of urban and suburban bus testing. Our activity at CNR IT Institute is also covering the naval sector. We have worked in the framework of the TESEO project on integrating hydrogen technologies on board of small yachts and boats. Especially, we have tested the hydrogen container on board. We have tested the fuel cell system. And this slide shows how these technologies can be integrated. The hydrogen container, the fuel cell system, the battery system can be integrated into the small yachts for naval applications. And this is a 250 kilowatt PEM fuel cell system to be used in naval applications. Very recently, we have started a cooperation with Fincantieri to assess hydrogen technologies on board of boats that are used as a hydrogen laboratory, as let's say laboratory to test these advanced technologies. And this boat called the Zeus, that is tested in the framework of the TechBIA project that is founded by the ministry, Italian Ministry of Economic Development, is consisting of a fuel cell system of 120 kilowatt on board with a hydrogen tank of 50 kilograms, allowing several hours, about 6 hours of navigation under complete autonomy at zero emissions. And with this, I have concluded my presentation, trying to provide an insights about the projects that we have carried in this field in the framework of hydrogen. And of course, this is a great opportunity for us to have some cooperation with the Japanese institutions. We already cooperate with ACE. I have already signed a cooperation agreement with ACE to work on polymer, electrolyte, membranes for fuel cells applications, and we are strongly open to cooperation with the Japanese institutions. Thank you very much for your kind attention.
Thank you very much, Nino, for your comprehensive talk again. And so now let's pass to the industrial perspective. So we will start with Shoei Matsuda from Toshiba, that he will present us the activity sorry, exactly from Toshiba Energy Systems and Solutions. And he will introduce us the activities on fuel cells and hydrogen with a special focus on mobility. Please, Matsuda-san.
Yeah, thank you very much to give me the chance to introduce our activity. Okay, I will share. Okay. Okay. かな？出ました？皆さん。Okay.
Yes, now it's okay.
Okay. It's working. あ、これでいい？大丈夫？大丈夫だ。So, Toshiba has more than 100 years of experience in delivering various technologies for energy and infrastructure systems. We all recognize, Toshiba engineers all recognize the urgent need to create a sustainable society. So Toshiba has been developing and deploying many zero carbon solutions. Today, I would like to explain our hydrogen related technologies. This is the history of fuel cells in Toshiba. As a research and development activity was started in research center in Toshiba in 1960s. And late 1970s, Toshiba decided fuel cell technology should be the business. So we started as business activity. And the event is mid-1980s. United Technology in US, who delivered fuel cells for Gemini Apollo Space Shuttle, the space program by NASA, and Ansaldo Italy and Toshiba Japan, three companies founded International Fuel Cells in US. These three companies cooperated and developed large-scale phosphoric acid type fuel cells. We built 11 megawatt system in Tokyo area in 1991. This unit showed 42 efficiency, higher heating value basis. However, in 1990s, gas turbine technology advanced so much, and combined cycle system with gas turbine and steam turbine showed higher efficiency than fuel cells. So our market changed to on-site combined heat and power systems. United Technology and Toshiba cooperated to develop and deliver a 200 kilowatt phosphoric acid type fuel cell systems. The name was PC25. We delivered more than about 300 units all over the world. And in 2000, after 2000, proton exchange membrane type advanced realistically. Toshiba decided to start a development activity because of its easy to use and cost potential, because operating temperature is low. Then we started our business for residential fuel cells. The name was NFM. We delivered from 2009 to 2017. The total delivered unit is over 80,000 units. They are under operation now. However, we stopped our business for NFM because Toshiba decided we are focusing on hydrogen-related activity. Today, we are still continuing maintenance and customer support business of NFM. However, we don't deliver anymore. Today, we are delivering the stationary PEM type hydrogen fuel cells systems, and also other hydrogen related products. This picture shows one example image of Toshiba's fuel cell business. Our most interested area is green hydrogen. So using the power-to-gas technology, the hydrogen, green hydrogen can be made. And also, we need to increase renewable energy. However, as you know, the renewable energy is very fluctuated, not stable. So that to keep good grid balance, grid quality, some adjustment system is required. So Toshiba considering the green hydrogen from renewable energy and also demand response from grid side makes hydrogen. It's good, very good solution for power companies and also hydrogen supply chains. The stocked hydrogen is to be delivered to a variety of places, and at each site, hydrogen is used to make electricity. For example, a CHP cogeneration, or mobility use, or large size industry uses. So stationary fuel cells, we are supplying 100 kilowatt type package type hydrogen fuel cell unit. And also, we are ready to supply few megawatt class hydrogen fuel cell systems. And today's topic is, I would like to explain, we started the fuel cell module for heavy duty mobility vehicles. This is the demonstrational plant, Fukushima Hydrogen Energy Research Field. This is a large-scale demonstration facility funded by government and produce hydrogen using solar panels and also the surplus energy from grid side. This facility can produce 1,200 normal cubic meter per day. And this hydrogen is supplied to several areas in Fukushima Prefecture, Japan. For example, soccer fields or gymnasiums or shopping centers like this. And also, in coming Tokyo Olympic Games, this hydrogen is transported to Tokyo area and shall be used for fuel cell buses to transport athletes. I hope it will happen. So this is our key technology. We are making, or we are developing and making from material basis to power generating system side. We have MEA manufacturing facility in-house and also cell stack assembling line in-house. We have a long history of system development and operation. So this technology can enable us reliable long life systems. This is our distinctive technology. We are using internal humidification systems for PEM fuel cells. PEM membrane have to be wet. So anode gas or cathode air, we have to humidify. So to this function, we are using porous separator or bipolar plate. Each separator, we have cooling water flow path. And this water can goes into the porous separator plate and makes gas seal and also from the surface of separator plate, the humidification is supplied. So the internal cell stack area in everywhere, fully humidified condition can be achieved. And on the other hand, in cathode side, by the reaction of fuel cell activity, fuel cell reaction, the water is made as some condensed water blocks the gas movement to catalyst area. So these condensed water have to be removed. This porous plate easily removes, sucks water, condensed water into the coolant flow side. So using this technology, we can control the condition of humidified condition inside the fuel cell stack. This enables long life and also the very low pressure drop characteristics. Oh, I have to mention about the demerit of this system. As you can realize, to make porous separator, the separator becomes relatively thick compared to other fuel cell supplier. It's our next developing target to make thinner porous separator. This picture shows the difference of fuel cells for vehicles and also fuel cells for stationary uses. The stationary fuel cell systems need very long lifetime, continuous operation at rated power. At least 10 years continuous operation. It means at least 80,000 hours continuous operation at rated power. On the other hand, for fuel cells, compact size and higher output is required. However, it requires lifetime maybe about 10,000 to 20,000 hours. It's very different. Based on this, our stationary fuel cell technology, Toshiba thought for heavy-duty mobility application, this technology may be suitable. On the other hand, fuel cell vehicle side, they are trying to extend their lifetime. Anyway, good competition is very good for technology advancement, I believe. So for first product, we started development activity funded by government subsidy. We decided to develop 200 kilowatt class fuel cell modules for heavy duty mobility vehicles like maritime application or railway application. Why we decided 200 is we had many people how much power is needed for such applications. So from the result, about 200 kilowatt per cargo of one train is proper. So we decided one unit shall be 200 kilowatt. However, for maritime usage, maybe few hundred to few megawatt is required. So we are going to design the multiple parallel operation availability. This is also the difference of operating range. And this graph shows the current density horizontal and the cell voltage vertical. Red line is general fuel cell characteristics, output characteristics. So you know the current of fuel cell stack is linear to hydrogen consumption because of the theory of self-active reaction. So to have the good efficiency, higher voltage is required. So we are trying to improve this red line upward. And for the compact size, current density is the right side, drawing side, extending to the right side. This is a development activity. For stationary usage, we need higher efficiency because the merit is higher efficiency than grid power supply. So operating area is relatively left side. For fuel cell vehicles, maximum power or idle or cruising power, the current density very wide range. However, the maximum power time is somehow limited. Generally, they operated about 30% of its rated power operation. For maritime usage application, continuous operation is required, and also the compactness is also required. However, we believe its space is larger than lightweight vehicles. This is difference. For such application, this is our experience. This is the 40-meter small ship operated in Tokyo Bay by Tokyo University of Marine Science and Technology. We started the cooperative development with this university from 2016. At first, we tried to install a residential unit itself, no change on this board. We installed 2 units of 3.5 kilowatt power output in 2 years. After operating in 2 years, we disassembled and checked and find no degradation or something, no problems. So we decided to start the development fuel cell on ships. Today, this ship has a 30 kilowatt unit on board and operating in Tokyo Bay. This is a major topic of our activity. This is also the government-funded activity. We made consortium, the ship owner of NYK Group and Toshiba Fuel Cell Supplier and Kawasaki Heavy Industries, who is supplying the hydrogen storage unit on board and the hydrogen supply system and also energy management system. And ENEOS is the largest oil and energy supplier in Japan. It's taking place for hydrogen supply system ground side. And Class NK, the certification body, who is contributing the safety testing or how to make a procedure to certify the ships. And we are going to start the ship operation in 2024. And this is the demonstration program. And I will show you the animation to explaining this activity. Just a moment, please. Oh. Oh, no, no. 切れた？
切れてないです。大丈夫です。
ここがちょっと邪魔なのが。動かない。ちょっとね、ボタンが。
その左のところのボタンを動かせばいいんですか？
ない。これでいいのか。
ダブルクリック、ダブルクリック。
これ動かないんだよな。ちょっと待って。一回動かしてから。これ隠れちゃった。
それをどうしたらいいんですか？
で、これをさっきの、なんで消えた？
いや、聞いてないです。それ以外ですか？デスクトップ。
あ、最後ね。これ消えない。So this animation is you can see in this site. And finally, in Toshiba, at the center of Toshiba, we have H, hydrogen. So my hope is hydrogen becomes the hydrogen business becomes the center of Toshiba's business. Thank you very much.
Thank you very much, Dr. Matsuda, for the very interesting talk. And now we are passing immediately to the other aspect from Italian side, another type of fuel cells, the high temperature fuel cells. So Dario Montinaro of Solid Power, he will show us his work on, the work of the company on solid oxide fuel cell and solid oxide electrolyzer. Please, Dario.
Good morning, everybody. Thank you, Mr. Ambassador and Enrico, for inviting me in this very nice event. It's a pleasure for me today to introduce our company and to show the progress we made in the last years on cogeneration and electrolysis application. I will give you a short introduction of the company structure and facilities. And I will talk about our product for cogeneration and for electrolysis, showing the last results mainly focus on electrolysis and co-electrolysis application. The history of our company starts almost 20 years ago with the start of the activities at the HD Ceramics, a spin-off of the École Polytechnique Fédérale de Lausanne. And in parallel, in the same years, we started some activities in Italy in another company. In 2007, SOFC Power, that was the former name of the company, was founded, and we acquired HD Ceramics with its technology. So the history of the company starts from 2000. We started the prototyping activity in Mezzo Lombardo, in Trentino area, with the first pilot plant equipped for manufacturing and testing stacks. The first large-scale demonstration of the cogeneration operation of our system in Europe started in 2014, thanks to the ENEFIL program. It was a European project where many of the main players in cogeneration in Europe started to install their system. So that was the first opportunity for us to demonstrate and to test the behavior and the long-term durability of our system in the field. In 2015, we acquired the facility of a former competitor of ceramic fuel cell Germany, that was actually starting from an Australian company, an historical company in the field of solid oxide fuel cells. And we restarted the commercialization of the BlueGen cogenerator in 2016. In these years, we combined the experience of SOFC Power and the team of CFCL, the former team of CFCL, to further develop the system and to start the commercialization of the current unit, which is what we call the BG15, BlueGen 15, which is our current product. Last update is 2020, when we started the new industrial manufacturing plant here in Italy. I will show you some details later in the presentation. So solid power is distributed in 4 countries, headquartered in Italy, where we have the historical site in Mezzo Lombardo and the large-scale production facility in Pergine, in Trentino area. We have a manufacturing plant in Germany. We have a prototyping and R&D facility in Switzerland, and another R&D facility in Australia, in Melbourne. The new industrial plant is designed for large-scale manufacturing of solid oxide fuel cells and stacks. Till a couple of years ago, one of the main challenge of distribution of solid oxide fuel cells technology over the Europe and the world was actually the large-scale manufacturing. And thanks to this progress in the manufacturing plant, we can produce up to 25 megawatt stacks yearly production into shift, and we have the potentiality to expand the production up to 50 megawatt per year. This is a fully automated plant, and it has the productivity today of more than 1 million pieces per year. This is 6,400 square meters of industrial space, excluding the buildings, the office buildings. And we started the production last year, in 2020, in August. So it is fully operating now. In this plant, we produce what we call the G8 stack, which is the core of our system. This is the product ready for the market. This is installed on the BG15, and it is a 1.7 kilowatt DC in fuel cell mode, consisting of 70 repeating elements with active area of 80 square centimeters. The technology behind it is based on solid oxide, anode supported solid oxide fuel cells made with conventional materials, nickel oxide, zirconia cermet, and perovskite based oxygen electrodes. On the prototyping level, we are working on a large scale stack for mainly for industrial application. This is a 8 kilowatt DC and consists of interconnect containing 4 cells. This scale-up approach helps to use the existing manufacturing facility, the already automated manufacturing facilities, and to use the same cells, sealing, and contact solution for both kind of stacks, for the small one and the big one. The production of this stack today was made on a prototyping level in Switzerland, in our lab in Verdun. And starting from this year, we are transferring the pilot production in Italy, in Mezzo Lombardo. Our current products are mainly designed for solid oxide fuel cell operation. Potentially, we can use several kinds of fuels, starting from natural gas, which is widely available for, especially for domestic and residential application. But potentially, we can also work with the liquid fuels, biofuels, hydrogen, and ammonia. And especially on research level, we are also investigating this kind of operation, and we are working on prototypes. Our product portfolio consists of 2 main units. The BG15, it's a 1.5 kilowatt unit for residential and small commercial application. And this is equipped with the G8 stack, the 1.5 kilowatt one. BG60 is the bigger unit, 6 kilowatt for small commercial and hotels and restaurants, and some other industrial application. And this is equipped with the G8X stack, so the large area design. So basically we have two kinds of stacks for two kinds of products today. The application are quite wide and include distributed generation and cogeneration, on-site hydrogen production, syngas production, and auxiliary power unit for marine application. With the large area stacks, we are moving to a new prototype, which is the large stack module. This is a 20 kilowatt stack module in fuel cell mode, working up to 75 kilowatt in electrolysis mode. Today, we are working to expand the power up to 100 kilowatt in electrolysis mode. This has been tested at DLR in a fuel cell mode in 2019, and it has been tested in the laboratory of CEA in 2020 in electrolysis mode, working as electrolyzer. And we demonstrated the productivity of this unit for about 50 kilo of hydrogen per day at 74 kilowatt energy consumption. Our market today is mainly concentrated in Europe, but we are also expanding to US and East. Today, we have installed more than 1,900 units in 12 countries, and we have demonstrated stack lifetime up to 7 years and totally above 37 million hours of operation. Other application consist of high temperature electrolysis. In this case, we can use electricity mainly from renewable sources and water to produce hydrogen, working in steam electrolysis mode, or synthetic fuels and hydrocarbons, working in co-electrolysis mode. We have investigated this operation mainly in the frame of European projects, and our experience on electrolysis starts 10 years ago in the frame of the other project, where we tested for the first time one of our stack in electrolysis mode for a durability test up to 10,000 hours with a very stable behavior. With the aim of combining the electrolyzer with the renewable sources, we have investigated the load cycling, typical from solar and wind sources. We have tested the first time this operation at lower temperature in the frame of the other project, but it was investigated also in the recent years in the frame of Sofia and ECO. In particular, in Sofia, we investigated load cycles in steam electrolysis and CO2 water co-electrolysis mode. We have observed a slight decrease of the performance due to cycling, but actually up to 11,000 cycles, the decrease of performance was just about 60 millivolt for a total of 5,200 hours, and roughly this corresponds to 30 years of operation with one cycle per day, which is more than necessary for this kind of application. So the stability of the system, even with load cycling in electrolysis and co-electrolysis mode, is very, very good. We have also tested durability in co-electrolysis mode in the frame of ECO project, and we have reached 15,000 hours of stable operation. Finally, we are moving to larger area stacks, to our module with the 75 kilowatt electrolyzer tested in CEA. We made a map monitoring the performance of the unit at different temperature, working close to thermoneutral voltage. In the frame of this test, we have demonstrated the productivity of 50 kilo per day of hydrogen at 745 degrees, and the potential to work up to 79% steam conversion with a 96% efficiency. Many of these research activities, especially on electrolysis, were done in the frame of European projects. So we thank the fuel cells and hydrogen joint undertaking for the support, and we also thank the local government and Department of Business, Energy, and Industrial Strategy. Some of our projects are dedicated to extend the lifetime cost reduction and field testing of cogenerators. This is the case of Ruby, Adastra, Low Cost, IC, New SOC, and PACE. These are still open projects. And many other projects are addressed to high temperature electrolysis and other applications. Some included in this slide, but there are many more. Thank you very much for your attention.
Thank you very much, Dario, for this nice overview. So now we can open the discussion. We don't have much time. And so I would like to start with a question, basically on pointing out I mean, the difference then Nino Arico has put in his title, green hydrogen, while Kazu has spoken more in general of green and gray. So I think that it is very important to make the difference between green, gray, or blue hydrogen with because of it, basically hydrogen it's a vector, it's an energy vector. It's not a primary source of energy, so it needs to be produced with a primary source. So as shown by Kazu, the next METI policy on green growth for the energy mix foreseen 10% hydrogen, which is separated from renewables or from I mean, for fossil fuels. I think, and this is a little bit misleading because, as I said, hydrogen is just an energy carrier. So it is important to understand which is the source for that. So basically, before Suga, the main hydrogen projects developed in Japan were in collaboration with Australia and Brunei in order to produce hydrogen for fossil fuels and then transport them to Japan. So I would like to listen about what do you think about this difference from hydrogen, I mean, from green and gray hydrogen, and especially, I mean, also Japan is thinking a lot about the use of CCUS, so carbon capture, utilization, and storage technology, which is unfortunately still far from commercial availability. So I'd like to first ask Kazu about what he's thinking about this topic.
Yeah, thank you very much for the good question. First of all, I would like to mention that I'm not a government officer.
Of course, I don't want to know I want to know your personal opinion. I don't want to know the policy, because we know the policy.
Yeah, of course. You made a very good question and comment, because I agree with you that, for example, renewables are actually the primary energy, and the nuclear is also primary energy, but hydrogen is a secondary energy carrier. So it is actually also misleading. I agree with you that in such a policy paper, primary energy and secondary energy should not be mixed. Yeah, but on the other hand, Japan is somehow in the difficult or the different situation compared to the Europe. For example, in Europe, you can also buy for example, green electricity, renewable electricity from neighboring countries. But Japan is, surrounded by the countries like China and Korea, including North Korea and so on. So we must import, the energy carriers. So, and that was also the reason why we have actually mixed both things, yeah, renewables and hydrogen. So, but that means this policy maker indicate that, first of all, most of the hydrogen may be also imported from the foreign countries rather than using the on-site, generating on-site from the renewables in our countries. So the reason why we have already stated that the 10% of the hydrogen and ammonia we will also use is that policy paper may also clarify the the scale of the hydrogen which must be also actually imported. Yeah, but on the other hand, the increasing companies like Toshiba has also strong interest for green hydrogen, and actually Mr. Matsuda made a presentation which is more compatible with the renewable energy technologies. So among the renewable electricity, I think part of such energy we will also convert it using electrolyzer technologies to be also used locally. So still we have the more centralized policy concept to import hydrogen, but with time we may also increase the fraction of green hydrogen. Yeah, I hope I can also answer to my to your question from my private viewpoint.
Absolutely, of course. I mean, this is the point. So I will ask first Matsuda-san also to have his point of view on this topic from Japanese side.
Oh, so it's also a very difficult question. This is my
point of view of the industry.
Point of my opinion. Using hydrogen is very good thing for people. So anyway, green or gray, the increase the hydrogen's consume is one path. In such cases, however, carbon capture is also important. In the case of carbon capture system, maybe gray hydrogen is a temporarily very good approach. This is my opinion. But finally, engineers must target green hydrogen. This is my opinion.
Thank you very much. Yes, basically, it's very difficult to reach zero emission in 2050 if we will continue to use fossil fuels. This is the problem. But for reducing, I totally agree with you that it's still better to use hydrogen than nothing. So now I will ask Nino for his opinion, but I mean, of course, the European point of view is clear that hydrogen should be green. Nino.
Yeah, Enrico, I personally believe that we need to urgently address issues of climate changes and global warming. So this is an urgent request to address these issues. So we need to move rapidly to green hydrogen and sustainable energy technologies in general. So there is not much time left. So it is, of course, blue hydrogen. Blue hydrogen means hydrogen from fossil fuels with carbon dioxide capture and sequestration could be useful in the transition period, but we need sustainable processes. So that means we do not have to delay moving towards green hydrogen. This is my personal opinion, but this is also the, let's say, position of the European Commission. In July, the European Commission has released a communication about the strategy, about hydrogen strategy. And if you take into account this communication, the focus is on green hydrogen, electrolysis, 40 plus 40 gigawatt at 2030, significant investment in this field. So hydrogen is already widely used in the chemical industry, you know, but this is gray hydrogen. We need to start replacing this gray hydrogen with green hydrogen, but the main issue is decreasing the cost. Actually, the cost of hydrogen in Europe is about 10 euro per kilogram. We need moving to 2-3 euro per kilogram in order to make this competitive with the fossil fuels, with steam reforming of natural gas to produce hydrogen. So this is really an urgent task. So this is my personal consideration about this topic.
Thank you very much, Nino. So I twist a little bit the question for Dario, because Dario is involved in developing solid oxide fuel cells. I mean, so high temperature technology, which can use other fuels with respect to only hydrogen, as he shows in his presentation. So this is particularly important also because one of the problems of the slow starting up of wide use of hydrogen is the difficulty in hydrogen storage and the transportation. So how do you see this topic in terms of, of the point of view, the high temperature technology, and with this point of view in mind, Dario?
Well, first of all, I agree that we have to give the right definition to green, gray, and other cores of energy. Describing the right energy source is mandatory, as well as it is mandatory to address all the efforts to the green energy. No doubt on that. However, in this transition period, due to some still technology limitation, let's say, which affect the storage and transport, as well the production in some cases of green hydrogen, we need to accept a transition to some alternative fuels, including gray hydrogen, of course.
Thank you very much. I also think that this is the advantage of solid oxide fuel cells, that may allow the use also of biomasses or other, partially green fuels, if not totally green. So I would like to ask a question now on mobility. We don't have much time, so for electrical vehicle mobilities, there is a debate about batteries or fuel cells. So which is better for cars? And so I would like to hear something now from Matsuda-san from a Japanese industrial point of view. Which do you think would be better for vehicle transportation, electrification with batteries or fuel cells?
So the battery technologies advances very rapidly. For lightweight vehicles or short-range transportation, the battery is very attractive. However, talking about for ships, battery ships can be operated maybe continuously 7 to 8 hours a day. and have to be charged almost same time in nighttime. However, in the case of Japan, coastal voyage route, ships operated about 30 to 40 hours continuously from Tokyo to Hokkaido or Nagoya to Kyushu Island. So in such cases, battery never happens. So I believe hydrogen or fuel cell and the batteries can exist in the future, mixed for suitable application. This is my impression.
Thank you very much. I have to say that I totally agree with you. And Nino, do you have something to say about mobility, since also you have studied for a long time polymeric fuel cells for cars?
Yeah, I agree with the comments from Dr. Matsuda. I think that, of course, for a city car, batteries have really are probably the best options. But since hydrogen is characterized by high energy density for ships, trains, buses, especially public buses, fuel cells are already competitive. So as an example, in Europe and in Italy, almost 30% of trains are diesel trains. And electrification of these routes is really hard to make. The cost of electrification is €1 million per kilometer. So this is very complicated to address. So hydrogen trains can be a solution for this. So Alstom and Snam in Italy are in Germany, and now in Italy are addressing this aspect. So we think that in the future we can replace diesel trains with hydrogen trains, and this could be already a cost-effective solution. Regarding ships, of course, it was already discussed by all speakers that fuel cells, hydrogen-fed fuel cells, are a useful option for ships. This is really an important option because, of course, hydrogen has these appropriate characteristics for these heavy-duty applications. So I think this approach, hydrogen technologies are already competitive for in this context. Of course, we need to decrease the cost of hydrogen. We need to decrease the cost of technologies. This is the priority at the moment to promote wide-scale application of hydrogen.
Thank you very much, Nino. I am very sorry, but I mean, we are running out of time. There would be many other questions, many different aspects, topics then we would like to discuss more, but it will be for another occasion, for next time. So I'm closing the webinar. First of all, I thank all the speakers for the very, very interesting and informative talks. Definitely, we need to find solutions for solving the climate change problems. And we need to find solutions, especially if we want to really reach zero emissions for 2050. So Italy and Japan are two countries that are at the forefront in this type of research, and there's a lot of space for possible collaborations and both at academic and industrial level. And I hope that this webinar will be a small contribution for pushing and improving these collaborations and joint activities. So thank you very much for everybody. Have a nice continuation of the day for people in Italy, and have a nice evening for everybody in Japan. Thank you. Bye-bye.
Thank you very much.
Bye.
Thank you very much. Bye.
Bye-bye.